started to consider the Hilbert action in the Palatini formalism, which is the first order formalism, where G mu nu and the Christoffel symbols are treated as independent fields, and we assume the torsionless condition, and we do not assume metric compatibility. We have seen that the variation of the action with respect to the metric gives the Einstein equations, and now we proceed to consider the variation of the action with respect to gamma. S is quadratic in gamma, so there are quadratic terms and linear terms, but the linear terms they contain derivatives, so let us add a boundary term, and we will isolate the boundary term from the rest. And remove the derivatives from the gammas. So, for example, here we have d lambda, d lambda acting on square root of minus g mu nu, gamma mu nu lambda. This is the first total derivative. And then from here, we have minus partial nu square root of minus g mu nu, gamma mu lambda lambda. These total derivatives give two contributions. One is the one that is obtained by making them act on gamma, which is the one we have. And then there is another one which is obtained by acting on the rest, and that we have to subtract. So we subtract partial lambda square root of minus g mu nu, gamma mu nu lambda. And then we add partial nu square root of minus g mu nu, gamma mu lambda lambda. And the final quadratic terms remain identical to what they are. So gamma mu nu alpha, gamma lambda alpha lambda, minus gamma lambda mu alpha, gamma mu alpha lambda. Okay, so this is the action. And now we can work out the field equations obtained by the variation with respect to the Christoffel symbols. And in those field equations, we can ignore the boundary terms, because they are boundary terms, and so the variation is zero at the boundary. And the rest I will leave to you as an exercise. So the exercise is to prove that the variation of the action with respect to the Christoffel symbols implies metric compatibility. Partial sigma g mu nu. Then, if we replace gamma with the solution of its own field equations inside the action, we switch from the first order formalism to the second order formalism. So we can define the Hilbert action as a functional of G only by taking that action and replacing gamma with the solution of its own field equation. And this is what you normally work with, I think. I don't know how it was presented in general relativity, but this is it. And again, when you study the field equations of the Hilbert action, remember that you do not need to vary gamma, even if it is a second order formalism, because you can write those as the variation of S, let's say G gamma, with gamma fixed, and then gamma replaced by its function of G, plus the variation of S, G gamma, with respect to the Christoffel symbols, say new indices alpha, beta, gamma, with G fixed, and then gamma replaced by its solution, field equations, times the variation of gamma, of alpha, beta, gamma of G, with respect to G mu nu. But the second thing, this thing is 0 because gamma of G, the solution, is precisely what makes this functional derivative vanish. And therefore, you can just write it like this. Which is what we did, so we do not need to do it again. And we studied the variation with respect to G mu nu with upper indices, but it doesn't really matter because it was simpler, but you can make the same argument in both cases. Of course, it's just a simple change of variables, switching from G mu nu with lower indices to G mu nu with upper indices, from the metric to its inverse. It doesn't concern the Christoffel symbols. What's interesting now is to do it, to write down this action. And there is a simple trick that allows us to do it very quickly. Actually, we don't need to do anything. And the trick is as follows, and it's very general for quadratic action. So this is, you see, a quadratic action in gamma. Let's ignore the boundary term because it will be a boundary term and we leave it there. This is linear. So now we prove in complete generality that when you work out the field equations of this action and you insert the solution back, it's just like changing the sign of this, with gamma replaced by gamma of G. So the entire procedure is very general. We can do it for a generic action. It doesn't need to be, we do not need to burden the argument with many indices. We just do it in generality. So let us consider a generic quadratic action where the variable we consider is appearing only algebraically with no derivative. So you will have, let's say, an action which is functional like this, some integral 1 over 2 chi m chi plus a chi plus b. Chi can have indices, it can be a vector, so you would want to write this as transpose. We don't do that in physics, normally it's understood, so you should understand this, something like that. Okay. So we just treat this as in matrix notation as a vector, matrix vector, the transpose, and we just keep track of the order of the objects, and if we do that, we do not make any mistake. If you take the variation with respect to chi, what is it? Well, here certainly the matrix M must be symmetric, so it doesn't matter where you take the variation, you have twice, that's why I put this 1/2. So you have M chi, vector notation, matrix vector, plus A. If you want, let me exchange the order here so that if this is clearer to you, we are ordering the variation delta chi to the left, and so that's A. So chi is a transpose if you want. And yeah, let's write it like that, why not? And that is 0. That means that chi is equal to minus m to the minus 1a. Minus m to the minus 1a. So let us see what we get when we replace chi with this solution inside the action. S of minus m, let's say S of chi, with chi equal to minus m minus 1a is equal to what? The integral of 1/2. So the transpose of that is minus a transpose m minus 1 transpose, but m is symmetric, so we can forget about the transpose there. And that's chi transpose. Then there is m, and then there is chi again, minus 1, and chi is m minus 1 a. There are two minus signs, and whatever. Then there is again chi transpose, which is minus a transpose, m minus 1 transpose, which is m minus 1, times a, plus b. So you see that here, m minus 1, let me use another color. So m minus 1 and m gave 1, minus and minus gave 1, and so you have 1/2 a transpose m minus 1a, which is exactly that one. And therefore, in total, you have minus 1/2 of that. So the result will be minus 1/2 a transpose m minus 1a plus b, which you can also write as minus 1/2 chi transpose m chi plus b, as long as you remember that chi now is replaced by its solution. So as you see, when you substitute the solution of this simple field equations, you just drop the linear term, you do not touch the zeroth order term, and you change sign to the quadratic term. So we don't need to work a lot. the result here, this action, which actually is SH of G, we call it, is equal to this boundary term, which we'll leave like that, and actually maybe we write it a little bit better. Then we drop this, and we just change these two signs. And that's it. So let's write SH of G. First, I change those two signs. So I write this, we have this, d for x times that. Changing the sign just means that instead of -1 divided by 2k squared, I just write 1 divided by 2k squared. 1 divided by 2k squared times that. So that's gamma mu alpha, gamma lambda lambda alpha. Minus gamma lambda mu alpha, gamma nu alpha lambda. Plus the boundary term, which we write in a certain notation, just to simplify it a little bit. We write it like this: d partial lambda w lambda. Let's see what w lambda is. We just read it from the expression here. So minus 1 divided by 2k squared, we leave it out. So partial lambda acts on this. And then here we just need to change the notation for the indices to have lambda. So nu will be lambda, and alpha lambda will be called something else. So square root of minus g, g mu nu gamma mu nu lambda, square root of minus g, g mu nu with upper indices, I guess. No? Yes? Guess so, let's check. Yes, minus square root of minus g, we can collect it. G mu lambda gamma alpha, gamma mu alpha alpha. Alpha alpha. The boundary term now will play no role, but later when we will study the boundary term of the in a covariant way, we will have to express the boundary term in a covariant way. We will come back to this formula, but that will be for the second part of the course. Probably this argument will be at the very end, because don't know if I will have time before. So basically one could say that this is the action, and that is known as gamma gamma action. So if you want, you could drop everything else. This is due to Einstein, I guess, and it is a non-covariant action which does reproduce the correct field equations, and actually has better features from the point of view of variational principle. Because here so far we have been cheating a little bit. And now we can address a problem. Now, normally when you have a Lagrangian, that is a Lagrangian of q dot, and then you build an action by integrating. Could be function of t actually also. So L of q of t, q dot of t, t dt. Fine. But that's what we normally do, both for the sake of the variational principle, which allows you to do what? For example, you can define your variation by keeping the values of the function fixed at the extrema. But you cannot keep the values of the function and the velocity fixed, both. So if this action goes, let's say, from t1 to t2, then you can say that q of t1 is fixed and q of t2 is fixed, some values. Then you do your variation. You cannot say that, you can, for example, do a variation with q1, q2 fixed, and q1 dot, q dot of t1 and q dot also fixed. Because if you fix positions and velocities, then you have only one trajectory. You don't have variations. You cannot find the field equations because the field equations. Yes, so here, what is the peculiarity of this action and why was it introduced, even if it's not covariant? It depends only on the first derivatives of the metric. Depends only on the first. On g mu nu and the derivatives of g mu nu. Like saying, so the first time derivative, not the second time derivatives. So it's like a Lagrangian as a function of positions and velocities. It doesn't depend on the second derivative, it's time. This is a non-trivial thing because in gravity, strictly speaking, when I wrote that, the Ricci tensor, that contains second derivatives with respect to time also. So that is an action that written like that has Lagrangian that depends on positions, velocities, and accelerations. So strictly speaking, every variation I've done so far was ill-defined. As a variational problem. We will come back at the end of the course, which will be at the beginning of May, because I think we will be able to end everything by the first days of May, because I have some conferences in May to attend. 54 hours and 36 plus 18. So. But we can anticipate a little bit because we have been doing a variation and probably nobody ever told you, and you will get used to do variations without caring about the boundary terms, and that is correct to some extent because actually these details turn out to be not particularly important in physics, and actually even when we added terms like r squared, Ricci squared and so on, there is a problem there because we cannot get rid of the higher derivatives there. So we will see what the fate of those higher derivatives and the meaning of those we will see, because that will be related to quantum gravity. But at least in classical gravity we do not have a problem because let's say this was just a temporary action. It is correct up to a boundary term. So let's say that was not the right action. Okay, that was not the right action, mathematically speaking, but there is a right action, although it's not written in a manifestly covariant way. And it differs from that just by a boundary term, which does not affect the field equations. And it is this one. So you can say, okay, but this is not covariant. Is there a way to write this is add here a boundary term, not this one, but a boundary term, or yes, maybe it will be a rewriting of that one, that makes it covariant completely. Yes, there is. So if you want to, if you are picky and you want to purify completely this variational problem from the mathematical point of view, from the point of view of the calculus of variations, it can be done. Okay, and we will see it at the very end. Because it requires a long construction. You would have to break your manifold into time and space because you have to reach the boundary, and normally the boundary is past and future. And so it opens a new chapter. It will require some lectures. So this is a nice action, actually, from many purposes. But just remember that gravity has this peculiarity. The first covariant action you write, the Hilbert one, the first one which was written, is not really, strictly speaking, the correct one from a mathematical point of view, but it gives the right field equations because the correct one, because the problem is all confined to a boundary term. So you can postpone the problem to, let's say, write everything in a manifestly covariant way and not care about it. There is no problem with Yang-Mills, because in Yang-Mills the curvature f mu nu depends only on the first derivatives. This is the peculiarity of gravity. In gravity, the curvature, which is the analog of the field strength, depends on second derivatives, the Riemann tensor, of the metric. First derivative, it always depends on the first derivatives of the connection. In Yang-Mills and in gravity, the curvature is always the same thing from the point of view of differential geometry. So it always depends on the first derivatives of the connection. But the point is that in QED or Yang-Mills, the connection is the field. Here it is not. The connection is just, yes, you can treat it as an independent field, but it is just there as an auxiliary field. It appears quadratically, it can be integrated out, and that's not the fundamental field that describes gravity, which is the metric, and not the connection. And so, in the end, R contains two derivatives. Now you can ask yourselves, and this is a peculiarity of gravity that is actually astonishing, because if you ask yourselves how many actions you can write down for Yang-Mills or QED. Well, you can write down infinitely many actions. They all functions of f, just f, without derivatives of f, will always depend on q and q dot. So it's like saying, okay, in mechanics I can have this, but I can also have this. It's a function of q dot. It's a complicated function, but relativity leads me to that function. But I could do the same for Yang-Mills or QED. Here, I guess it's the determinant of flat space. Guess it is like this, but I don't really remember if I'm doing everything correctly. This is called Born-Infeld action. I quote it if you want to check if I wrote it everything right. But any function, so here you can have any function of q dot squared, let's say, okay, if you want to be pure, have invariance under the change of the direction of time. And here, to have gauge invariance and be sure, you can consider any function of f mu squared. They will always be good actions from the point of view of the variational principles. Now, if you ask yourselves how many good actions there are for gravity, there is only one. And that's a property that no other theory shares. And that is the one, the Hilbert action, which is not correct, but just for the boundary term. And so in the end, it's the only one that is correct. Because anything you can build, anything else you can build will violate this property. So the only action that can describe gravity by means of the Lagrangian, that up to a total derivative, because we know the Lagrangians matter up to total derivatives. With the Lagrangian that only depends on q and q dot is this action. So the action of gravity is unique, plus the cosmological term, of course, if you want. And so the action of classical gravity is unique. Unfortunately, this action is not good for quantum gravity, and then the problem will reopen and reappear, because this is for sure that this action does not lead to a good theory of quantum gravity, for the reasons that we will see next week probably. So classical gravity has a unique action. This is, I would say, unprecedented. Okay. Another peculiarity of gravity is that in gravity, there are no local invariants. Invariance with respect to what? Invariance with respect to diffeomorphisms. Here we are not using the field bind, so we can forget about local Lorentz transformations, but even in case, it just have to have invariance under both local Lorentz transformations and diffeomorphisms. So for example, a scalar you could say it's an invariant. Well, it's not an invariant. It does change. And we know that at the infinitesimal level, delta phi is something like that. Don't remember if I had a minus or not. Maybe not. No, I think not. So it does change. It's not an invariant. Instead, f mu nu is a local invariant. What do I mean by local? Something that depends on x and it's invariant in the point x. So it's not taken to another point. Unfortunately, a change of coordinates takes to another point. So that's why you then don't have local invariance. So if you compare a scalar in the same point, phi prime in x and phi in x, you know that we have a difference. That's why it's not a local invariant. And f mu instead is a local invariant under what? Not under diffeomorphisms, because it cannot be, but under gauge transformations. So that's why we say that there are no local invariants in gravity, which means with respect to the symmetries of gravity that are required local symmetries of gravity. So this, in every x, is invariant under gauge transformations. But to build invariance in gravity, you need to integrate on the manifold. Like the Chern-Simons. That's the connection we anticipated yesterday. Scalars, we integrate scalar densities actually, which means with the square root of minus g around on the manifold. Which means that you have the integral m d for x square root of g phi of x, where phi of x is a scalar. Any scalar. It could be r, the Ricci scalar, r squared, r mu nu, any scalar you want. Could be cosmological constant, could be the action of a scalar field, which I have to write with a different phi, and so on. So what is the infinitesimal transformation of the Lagrangian? Let's say this is the Lagrangian, square root of minus g phi. And the infinitesimal transformation of phi is the one we wrote. The infinitesimal transformation of g mu nu is the one we know, which is the Lie derivative. And that can also, yeah, this is useful here. We saw that we could also write it like that. So what is the variation of the square root of minus g? Well, it's 1 divided by twice the square root of minus g times the variation of minus g, which is minus g times the inverse times the variation of g mu nu. So that is square root of minus g divided by 2 times g mu nu and times that thing that we wrote, del mu psi nu, and by symmetry that is multiplied by 2, so the factor 2 goes away. So we can work out the infinitesimal variation of every Lagrangian. This is a generic Lagrangian. And so that's square root of minus g times the variation of phi plus phi times the variation of square root of minus g. And the variation of square root of minus g is this. So square root of minus g, g mu nu del mu x nu. Phi. Now, we know that the covariant derivative of a scalar is equal to its derivative, so and the covariant derivative of the metric is 0. So now let's check. We can write this as square root of minus g of a covariant derivative of something. G mu nu psi nu phi. Let's check. So if del x on phi, it multiplies psi with an upper index mu, which is correct. If del x on g mu, it gives 0, because we are assuming metric compatibility. And if del mu x on psi mu, we have the other thing. So this is the square root of minus g del mu psi mu phi. And you know that there is an identity that tells you that this is a total derivative, where you exchange the covariant derivative with a simple derivative. You exchange it with square root of minus g, and then it becomes a simple derivative. So that means that this kind of variations do not change the Lagrangian, because when you make a variational, apply the variational principle, so basically now the variation, the parameter of the variation is x psi, this psi. At the boundary or at infinity, your variation should be 0, and so that means that the variation should be 0. And in the variation of an action, because the variation of the Lagrangian is a total derivative, the variation of the action will be a contribution of the boundary, but a contribution of the boundary where you have the variation of something, your field, or here the coordinates at the boundary. So if your manifold has a boundary, the variation should be 0. Compact with a boundary, the variation should be 0 at the boundary. If the manifold doesn't have a boundary, the variation should decrease sufficiently fast at the boundary, and you have to define everything you do in the space of configurations where the metric, actually the difference, typically the difference between the metric and the flat space metric decreases sufficiently fast at infinity. And that is what we will start to do today or tomorrow, when we will study the expansion around flat space to move to quantum gravity. But before doing that, let's complete the classical part, because we have been studying the coupling of matter to gravity. We have been studying gravity, and now it's time to put the two things together. It's simple, but we have to do it, because you might have seen it already, but certainly you didn't see it with fermions. That's the energy momentum tensor. So the action, now we will assume torsionless condition and metric compatibility without even saying that, because that's what is normally done. People who studied all options, there are people who studied the other options, normally they lead to very complicated situations, but they have some interest. So let's say that we take the action, add the cosmological term, and add the matter part, whatever it is. The energy momentum tensor is a tensor that's defined as follows. it's 2 divided by the square root of minus g times the variation of the matter part with respect to g mu nu. Now, observe that here I have g mu nu with upper indices. Then, since it is a variation and delta g mu nu with upper indices appears in the denominator, the resulting tensor is a tensor with lower indices. Because that's lower. That's upper in the denominator, means lower. And if you want to write it instead as a derivative with respect to the metric tensor with lower indices, then you will have a stress tensor with upper indices, and the only difference is a minus sign because you are differentiating with respect to the metric or the inverse metric, so you can check it by yourself. The difference is only a minus sign. We know how to work out the variation, in particular with respect to this, of the matter, of the non-matter part, the gravity part, because we know that we do not need to touch the Ricci tensor, so we can write that as g mu nu r mu nu, and we do not need to go inside r mu nu. Because that would give the field equations of gamma. If you're not convinced about that, you could play a little bit of tricks, because you can say, here there is gamma. What if I use the first order formalism, which means now that I have matter, I can use the first order formalism, but gamma could be also inside matter. To avoid any problem, the gamma inside matter, just replace that gamma with the Levi-Civita connection. So there is no other gamma but here, and then the field equation of gamma will again return that gamma is equal to the Levi-Civita connection. You have some freedom here. Whenever you have gamma, you can either always replace it with a Levi-Civita connection or replace it everywhere but here. It won't change much. You could also not replace it anywhere with anything, and then you will have something interesting, something new. If you keep gamma independent here, with fermions, for example, you will have something, but not particularly meaningful at the end. So this is just to say that if we work with the second order formalism, which means that gamma is gamma of g, we still do not need to make any variation with respect to g inside r mu nu. So let's study the field equations, the variation with respect to g mu nu, or let's see, yes, maybe 2 minutes. Just write it down. With upper indices, that's 1 minus 1 divided by 2k squared. So that's exactly what we had before. This is what we had before. And the only thing we need to add is the variation of Sm, whatever it is, with respect to g mu nu. Here I've written it with an integral. Let me write it with an integral. Indeed, let me leave the integral there because I need it. So what we do is to write not the functional derivative, but the variation, that's what we need. Delta S. Delta S will be, well, if you want, you can write it. I didn't maybe introduce this notion of functional derivative, but the functional derivative is just the object that in the variation multiplies the variation and the integral to give the result. So maybe I've never paused a moment to make this comment, but whenever you write a variation, and it's always an integral of the variation of your field or coordinate times something, that something is called functional derivative. This thing, whatever it is called functional derivative, and essentially it's the Euler-Lagrange equation. So, not really a new notion of derivative, but has a name that makes it appear very profound. Functional derivative. It's just this. Okay, let's stop 10 minutes and we will be back.